All right, so here we go with section 15.6, directional derivatives and the gradient vector. So take a minute, pause the video, and read this little paragraph here with this example from the book. So what this is telling you is, say you're in Las Vegas and you want to see how the temperature is changing. This is a temperature map. And we had the ability to go in the x direction or the y direction, but we never have had the ability to go like, let's say I want to see how it's changing as I move towards San Francisco, like in a different angle. And so we're going to find the directional derivative. And so that will allow you to go in whatever direction you like. All right, so here we go. So remember that fx and fy, the derivatives with respect to x and y of a function, represent the change in the x and the y directions. And you can use these to find a tangent plane to a point that is determined by the changes in the x and y directions. But if we want to go in a different direction, we need what is called a directional derivative. Okay, so our goal is to find the rate of change on a surface or a function in the direction of any unit vector that we name u equals ab. So remember, unit vector, so we have to divide out its own magnitude if it's not already a unit vector. All right, so below is how we do it. And the notation for directional derivative is this d sub u, and because that u comes from this piece right here, and d sub u of f of xy. All right, so here we go. So d sub u f of xy is equal to fx of xy, so the derivative with respect to x in the direction of, in the x direction of the function xy, and then times a plus fy of xy times b. Well, this is kind of similar to like the linearization and things that we did before and all that kind of stuff, so you can see it looks similar. Anyway, so you can kind of shorten this a little bit, fx times a plus fy times b. So hopefully you see that really you're just like multiplying the directions, the ab, by the derivatives. And so if I pull this apart and make it a vector with fx and fy, that is the derivatives, and then dot product it with a and b, which is a direction, that it is just a dot product. And instead of ab, we can also just put u right there. So I could further say this is just fx, fy dotted with u. And make sure you know that u is a unit vector, or you will not get the right answer. All right, so that is basically your definition of a directional derivative. That little last piece right there. All right, so moving on. So we're going to do that here. Now it's important to note that make sure it's a unit vector. And so this one says we have f of xy equals x to the third minus 3xy plus 4y squared. We're going to need fx, so that's going to be 3x squared minus 3y. We're going to need fy, so that's going to be, let's see, negative 3x plus 8y. We're going to need to plug in 1 and 2 into those things. So you plug in 1, you get 3 minus 3 times 2 is 6, so you get negative 3. And then we'll get negative 3 plus 16, so negative 13. No, positive 13. All right, and we will also need our unit vector. Well, go back to your unit circle. If you want something going at pi over 6, so you want something at a 30-degree angle, the perfect unit vector is square root 3 over 2 and 1/2, because that is a vector to the point here. It has an angle of pi over 6, and it is 1 unit long because it was off of the unit circle. So if you do the magnitude of that vector, it will be 1 because it came off the unit circle. All right, so we are just going to do our directional derivative at 1, 2. So I will have to dot negative 3, 13, dot that with my radical 3 over 2 and 1/2. All right, so we get negative 3 radical 3 over 2 plus basically 13 over 2. And you could calculate that to a decimal or whatever, but remember, it is just a single number. It is the derivative at that point in this direction, in a direction of 30 degrees off of that point. So it is just a number. Remember, it's just basically like the velocity going off in that direction. All right, so we're going to direct for this function here. It says for pi over 4, so we will be using radical 2 over 2 and radical 2 over 2 for our unit vector. And so the trouble here is I have to do the derivative. So I forgot my f right here. So fx, I'm going to treat that square root as a 1/2 power. So 1/2, 1 minus x squared over 4 minus y squared over 9 to the negative 1/2. And then let's see, times the derivative with respect to x inside. So it'd be negative 2x over 4. So I'll just say negative 1/2 x, or x over 2. And the same thing for y. Looks pretty similar. But I have to do the derivative with respect to y inside. So I will get times negative 2/9 with my y. All right, I have to do this at the point 0, 2. So what's nice about the fx is that I have a multiplier of x right here. And so that right there is going to turn to 0, which makes the whole thing 0. Well, for y, I do not have that case, but at least the x does go away in the center there. So I will have 1/2 times inside. I'm getting y squared, so I have 4/9 right there. 1 minus 4/9 is 5/9. So I have 5/9 to the negative 1/2. And on the outside, I have negative 2/9, let's see, times 2, so negative 4/9. So let's just clean that up a bit. My negative 1/2 on the 5/9, negative 1/2 power, is going to flip it over, so it's going to be 9/5, and the square root will be turned into 3 over radical 5 when I do my square root, times 1/2 times negative 4/9. So with some cancellation, that's 1 and that's 3. That's 2 and that's 1. So I end up here with negative 2 over 3 radical 5. So I just have to dot product this directional vector here, let's see, of 0 and negative 2 over 3 radical 5. I won't rationalize it now because I'm about to finish off the problem. And then times radical 2 over 2 and radical 2 over 2. All right. And when I do this, the first part goes away because it's 0, but the second part I get negative 2 radical 2 over, let's see, 6 radical 5. So of course the 2 and the 6 reduce to a 1 and a 3. So if I rationalize, multiplying by radical 5 over radical 5, I would get negative radical 10 over 15. And that would be my directional derivative in the direction of 45 degrees from the point 0, 2. All right, so I don't know if your papers are out of order or not, but this next page, oops, not that page. Crud. Let me see, hang on a second. Oh, so I wanted this to be the next page. Sorry about that. And so, I don't know, I got them out of order myself. So anyway, let's talk about this, then we'll go back and talk about those other 2 pages. All right, so the gradient vector. The vector that we used earlier in our directional derivative, this vector here that was fx and fy, that is used so much. Oops, fy. It gets its own little name there. That is called the gradient of f. So that is called the gradient vector. It has its own special name. All right, so the gradient of f is this thing, fx comma fy. And it also has a special notation. Do you guys know how in physics, how you see like delta x because it's like the change in x? Well, there's a new thing. This one is called del f. That little upside down triangle that you're used to writing the other way, you say that del f. So del f is the gradient vector. Okay, it's just basically 2 derivatives in each direction and put in a vector form. So if somebody, like in this next example, says to find del f at this place, we're just going to do what we've done before. It's just a different way of asking the same thing. So I'm going to find fx and fy, plug in my numbers, and there will be del f right there for me. So derivative with respect to x, I will get cosine x plus e to the xy, and then xy's derivative with respect to x would be y, so I'll put that here. And then sine x for fy goes away, so I'll just have e to the xy times x, because the derivative with respect to y. All right, so I have to plug in 0, 1 into these things. So, of course, cosine of 0 is 1, And here I get 1 times e to the 0, so it's also 1, so 1 plus 1 is 2. And over here I do have a multiplier of 0 right there, so this whole thing will go to 0. So my del f of 0, or at 0, 1, so my gradient vector at 0, 1 is 2, 0. Okay, so before we go to this next part, I want you to remember an old formula that we had that we'll talk about, and that is this one. Cosine of your angle between two vectors is the dot product over the magnitudes multiplied together. Okay, so remember, this is the angle between the vectors u and v, so that's going to be important in a second. So we have a special notation for gradient vector that was part of our directional derivative. We can rewrite our equation for the directional derivative if we want to. So du of xy, I need an fxy in here, is del f, okay, at xy dot u. So that's what we had before. All right, so it's just a gradient vector, just this new notation right here for that. So no big deal. And so what we're going to tie it to, is we're going to tie it back to this piece right here. Well, the dot product, if I move those magnitudes to the other side, would be the magnitudes multiplied by the cosine of the angle. So I would take the magnitude of these two things. So the magnitude of my del f times the magnitude of u times the cosine of the angle. Now remember, this has to be the angle. It can't just be any old angle. It has to be the angle between del f and u. So the problem has to be given to you in a special way, or a specific way. And so, you know, we know that u is a unit vector, so this is just equal to 1. So really what I have here is I have that my directional derivative of fxy. Another way to approach it is to do the magnitude of del f times the cosine of the angle. Now, like I said, the angle has to be given to you in a specific way. So don't go thinking that like on these problems that we just did before. All right, so on this problem here, on both of these, we got told that our angle was pi over 6, and our angle here was pi over 4. We were not, that was the angle we were trying to go. That was not the angle between u and the actual directional derivative, okay? Or I'm sorry, and del f. So it wasn't given to us in that specific way. So let me show you why that doesn't work. So, for example, this is what we just came up with. Okay, and you know, this first example that I was just showing you on the last page, it tells you pi over 6. So you can't just go plugging in pi over 6 into this problem. You know, we came up with the -3 and 13. You saw that on the last page. All right, you saw that like right here, right? And then you can just multiply by the cosine of pi over 6. Cosine of pi over 6 is radical 3 over 2. And so you can see that you're not going to get the same thing. If we did that right now, yeah, it would not come out to what we are supposed to get, which is this right here. Okay. All right. So what we have to do, so for instance, if we knew the magnitude of the 3 and the 13 to be 9 and 169 added together, square root times radical 3 over 2, that is not equal to that. So what you would have to do is a couple things. So it turns out to be kind of annoying. You would have to, first of all, use your cosine formula to figure out the angle between del f and u. And so I plug that into the formula here. And then basically what I'm doing here, so this answer that I get right there can be simplified to here. So the cosine at my angle is that. So what I'm doing is going back and putting it into the formula we created. I have my -3 and my 13 vector. And then the cosine of the angle, I didn't find the angle because I was going to need the cosine of the angle, and I already had it right here. So I just put that back in. So when you put that all through and simplify it, you do get the same answer. But that's because we found the angle between the two vectors. And so you have to be careful of how you're given the problem. And frankly, most of the time, you just can't really use this formula because of the way the problem is posed to you. Okay, so I'm going to do one more example, and then we're going to stop the video. I know I said 12 minutes, but let's just finish this one right here, and then we'll be good to go for class. All right, so for this one, this has more variables, so I'm going to need three three derivatives, fx, fy, and fz. All right, so fx here would be basically just sine yz. Fy, the x would stay. The derivative of sine would be cosine of yz. And then derivative of yz with respect to y would be just z. All right, and then let's see, derivative with respect to z. So the x would stay. I'd get cosine of yz and then times y. All right, so I need to plug in 1, 3, and 0 here. So you plug in 1 for x, 0 for z, and 3 for y. So you'd be getting the sign of 0 up top, so you get 0. Down here, I get a z as a multiplier again here, so I have times 0, so 0. And then here I have the cosine of 0, which is 1. X in front is 1, and finally y is 3, so I do get 3. And the only problem here, I am not given a unit vector. This is the vector 1, 2, and negative 1. This is not a unit vector. So I need to find its magnitude, which would be 1 plus 4 plus 1. So that'd be square root of 6. I need to turn this into a unit vector. So my u vector is 1 over radical 6, 2 over radical 6, and my negative 1 over radical 6. So just be careful of that. So I basically just need to dot these two, 0, 0, and 3. Dot that with the sky here, 1 over radical 6, 2 over radical 6, and negative 1 over radical 6. So luckily, the first two numbers turn into 0. So the last one is negative 3 over radical 6 dotted. And so if I rationalize, I would get negative 3 radical 6 over 6, which turns into negative radical 6 over 2. And there is my directional derivative. And that is it. I will see you in class. Bye-bye.